This is lesson 46, BHDL example 27, in which we'll implement a 4-bit adder. You recall from lesson 45 that these were the logic equations we derived for a full adder. This was the output S, and this was the output carry, inputs AI, BI, and the carry in. Here's the block diagram for the full adder. AI, BI, CI in, SI, and CI plus 1 out. And this was the logic circuit we had for a 4-bit adder. 0 carry coming in, we're adding A3, A2, A1, A0 to B3, B2, B1, B0, getting the outputs sum S3, S2, S1, S0, and C4 is the carry out. So the inputs will be A and B, and the outputs will be S and the carry out, and we'll also compute the overflow. You remember that was the exclusive OR of the carry C3 and C4 in this case, and we'll need a signal for these internal signals C1, C2, C3. So let's write a 4-bit adder VHDL program. Here's the entity, input A, standard logic vector 3 down to 0, input B 3 down to 0. The outputs will be the carry flag, CF, the overflow flag, OVF, and the output sum S 3 down to 0. So here's how we can write the logic equations sort of all at once. C0 is 0, that's for the rightmost least significant bit. And then we just write the S. Remember, S is 3 down to 0, A is 3 down to 0, B is 3 down to 0. We'll need the signal C, which is 4 down to 0, because remember we have a CI plus 1 coming out. So C 3 down to 0, well, S is just A exclusive OR with B exclusive OR with C 3 down to 0. So this logic equation is really 4 equations. One's for S0, S1, S2, and S3. And then here's the carry out. So this is really the CI plus 1. So notice how we write C4 down to 1 gets A and B. These are each 3 down to 0. Or this was the C in, CI, which is C3 down to 0, ANDed with A exclusive OR with B. So again, this is 4 different equations. So the first one would be C4 gets A3 and B3, or C3 ANDed with A3 exclusive OR with B3, and so forth all the way down to C1 gets A0 and B0, or C0 ANDed with A0 exclusive OR with B0. So again, this reduces to 4 equations. The carry flag is just C4, and the overflow flag, remember, is the C3 exclusive OR with C4. The simulation shows that in fact it works. Here we're going to add A. We made a binary counter, counts from say 1 to F shown here. B we'll set to the hex value B, or 11. So 1 plus 11 is 12, or C. 2 plus B is D. And notice this carry and overflow flag is shown here. 4 plus 11 is 15, or F. 5 plus 11 is 16, which is 0 plus a carry. So now the carry bit goes high here as soon as we get to 16, because it's 4-bit numbers. The carry bit stays high. Thinking signed, B is minus 5. So if we add 1 to minus 5, we get minus 4, which is C. We add 4 to minus 5, we get minus 1, which is F, 2's complement. But notice if we add 5 to minus 5, we get 0, which is correct, all the way up until 8. But notice these are positive sign numbers, but as soon as we get to 8, that's the same as minus 8 as a 4-bit 2's complement number. So this is minus 8 minus 5. So the correct answer then is minus 13, but we show 3 here, so that's wrong. So the overflow flag, you see, gets set. And you can compare the C3 and C4 all the way along here, and you can verify that the overflow flag is the exclusive OR of C4 and C3. So the simulation seems to work. You can then design a top-level design using that adder 4 component along with the X7 SIG, and then you can add the top 4 switches to the rightmost 4 switches, and you can have the sum displayed on the 7-segment display. The sum 3 down to 0 will be the rightmost digit. For the next digit, we'll take the carry flag, add 3 leading zeros, so if you get a 1, it will show up as the carry flag in X4 here. And then we'll show the switch numbers actually on the leftmost 2 7-segment displays. So switch 7 down to 4 goes into the high 4 bits of X, and then switch 3 down to 0 goes in the next 4. So remember, this 16-bit hex digit is what gets displayed on the 7-segment displays. And the overflow flag will display an LD0. So it's easy to write the top level design then. We'll have, this should be an M clock really, button switches LD, A to G, AN, and decimal point. And then you just add the components, adder 4A, X7 SIG, and then you'll have the signals X, 16-bit signal X, signal carry flag, signal S 4 down to 0. So X15 down to 12 gets the leftmost 4 switches. X11 to 8 gets the rightmost 4 switches. 7 down to 4 gets the carry flag, concatenated with 3 leading zeros. And then the sum is on the rightmost 7-segment display. And then you just port map the adder 4 and port map X7 SIG in the usual way. And you can then take this top-level design, download it to your FPGA board, and check by adding the 4-bit switches, leftmost switches to the rightmost switches, and observe the sum and the carry and the overflow bits.